Welcome back. Now in previous videos we have started with dipole moments. You know definition and some important aspects are related with these dipole moments. I hope you don't have any problem related to this phenomenon because this part we already discussed in a dipole moment. Okay. Now what happened in the next videos? See in this video. Now we are moving toward the next and VVIMP part of this topic again, that one is called the application of dipole moment. Application, because I know in JEE Main or Advanced or NEET examination they definitely ask you the question by considering their application of dipole moment. So which are the application of dipole moment? See toward the board. Now I am with application of, what is the applications of dipole moment? Applications of what? Dipole moment. Now dear students, so which are the applications of dipole moment? See toward the board. Now the first application, to determine the polarity and geometry of molecule. This is the first application of dipole moment, to determine geometry, to determine the geometry and this is another important thing, geometry and polarity of molecules. So this is the important aspects related to the dipole moment, to determine the geometry and polarity of molecule. Now dear students, what happened in this application? If mu is equal to 0, you know very well, if suppose if mu is equal to 0, then the molecule is non-polar, obviously, then the molecule is non-polar and that molecule is called as the symmetrical. Symmetrical means what? Which have a regular geometry. Then the molecule is non-polar and that molecule is symmetrical. The example of this is CO2, BF3, CCl4, PCl5, SF6, etc. So this is the first and very interesting phenomenon related to the application of dipole moment, to determine the geometry and polarity of molecule. The second one, if mu is not equal to 0, then what we say that, suppose for example, if we have a if mu is not equal to 0, then what happen here? Then molecule is polar and what? Polar and the molecule is unsymmetrical. So this is the very interesting phenomenon. For example, if we consider water, for example, if we consider ammonia, you see the lone pair containing molecule is there. Suppose for example, water, ammonia, we have a SO2, suppose for example CS3Cl, another example we consider here CHCl3, etc. So many example we consider because this molecule is non-polar. Listen very carefully. Those molecules which have a regular geometry means what? Regular geometry means even though this have a regular geometry, but all bonds is not same bond. Na? Regular geometry means all bonds are identical. The bond must be have the identical, then at that time we consider this phenomenon. Now dear student, the next important things, listen once again, listen. In previous videos I used one word, those molecules which have a regular geometry and normal bond angle, dipole moment of that molecule is 0. But what time? They must be have the same bond, like CCl4 all chlorine, for example PCl5 all chlorine, for example SF6 all fluorine, etc. Okay, so you keep in your mind, this is very interesting word. So this is the first application to determine the geometry of molecule. Now dear student, the second application of dipole moment, to calculate the percent ionic character. This is the second application, to calculate the percent ionic character. So this is the second application which we considered here in the dipole moment. So listen dear student, the percent ionic character is equal to, listen, this is a formula, the percent ionic character is equal to, how to calculate the percent ionic character? Experimental value of mu. See, this is the very interesting formula. Experimental value of mu, listen very carefully, experimental value of mu divided by theoretical value of mu. See, experimental value divided by theoretical value of mu, and finally into we considered here 100. So this is the percent ionic character which we consider this phenomenon, that is percent ionic character is equal to experimental value of mu divided by theoretical value of mu into 100. On the basis of this formula, I will give you one problem to you. Listen very carefully, dear student. Suppose the problem, write down problem in your notebook. Calculate the mu of HCl if bond distance is 1.34 angstrom. Listen, the problem is like this problem. Calculate mu of HCl if bond distance is, bond distance is, see the bond distance they are given, that one is called as the 1.34 angstrom. And dear student, and they are given the charge, and the charge is 4.8 into 10 raised to minus 10 ESU. Charge is 4.8 into 10 raised to minus, and calculate percent ionic character, and see calculate percent ionic character, calculate the percent ionic character if theoretical value of mu is, sorry, if experimental value, not theoretical we calculate, if experimental value of mu is, they are given 1.08 D. So these are the given data. Now dear student, you know that you just first calculate theoretical value of mu. How we calculate? Mu is equal to Q into D. This is a formula. By using that we calculate theoretical value. You know very well Q means what? Charge. They are charge given in ESU. So what you convert that ESU into the centimeter, because the unit of this is, so what happen is equal, what happen in this case, mu is equal to Q means 4.8 into 10 raised to minus 10, and into they are given the distance is 1.34 angstrom to centimeter, 1.34 into 10 raised to minus 8, because angstrom we convert into centimeter. Then after multiplication of this, the value of mu is equal to ESU centimeter. Okay, therefore 6.4 into 10 raised to minus 18 ESU centimeter. Okay, this is a theoretical value. Now how to calculate the percent ionic character? Therefore percent ionic character is equal to, you have a formula, experimental value divided by theoretical value. They are given to you experimental value, into 100, experimental value they are given 1.08 D. So therefore 1.08 D divided by 1.08 D, or we convert it divided by 6.4 into 10 raised to minus 18 ESU, 1.08 D, 6.4 into, and you clear the unit into 100, and then finally the answer of this becomes 16.79%. You calculate at your home, you manage the unit. So this is the second application by using that to calculate the percent ionic character. Dear students, so first application to determine the geometry and polarity of molecule, the second application to calculate the percent ionic character. Now we are moving toward the next and very interesting application to distinguish between cis and form of this molecule. Now friends, all you know what is the meaning of cis form and what is the meaning of trans form, because cis and trans form, besides cis and trans form, this concept we are already discussed in the general organic chemistry. You know, cis and trans, these two are the stereoisomer, and in stereoisomer these are the geometrical isomer. What is the meaning of cis? When two similar group is on the same side, then such molecule is called as the cis form, and whenever two similar group is on the opposite side, and then molecule is called as the trans form. So third application to distinguish cis form and trans form, listen very carefully, to distinguish what? Distinguish cis and which form? Trans form. Dear students, what happen here? How to distinguish between cis and trans form? Suppose I have this molecule C double bond C, I have here H, and here Cl, and here Cl, dear students, and suppose I have C double bond C, here H, and suppose I have here Cl, here Cl. You see, suppose now these two groups is similar, these two similar, therefore the configuration of this molecule is cis and configuration of this molecule is trans. Then how to decide the dipole moment of cis and trans are how to identify the cis and trans by using their dipole moment. This concept is very important. Now, by considering dipole moment phenomenon, less electronegative to more electronegative, electropositive to electronegative. So this is the sign. Both have a same direction, and this is this is the sign, and this is the sign, less electronegative to more electronegative. Now, dear student, both have a equal direction. It means that magnitude is different, but magnitude of both is same. This both is same, but with magnitude, sign is also same. It means addition takes place of all this bond. But what happened in transform? This is the magnitude and this is the magnitude. It means if it is plus 0.5, then it is minus 0.5. Then for dipole moment is cancelled. It means that mu is equal to 0 and mu is not equal to 0. It means what indicate this? If the cis molecule is there, then dipole moment of cis compound is always higher than the trans isomer. Is it okay? Dipole moment of cis isomer is always higher than the trans isomer. We cannot say 0. In this case 0, but higher than the trans isomer. Means what? Suppose for example, another example, CH3 bond C double bond C bond CH2 bond CH3. Suppose I have H, I have H. This is a cis isomer. This is cis isomer. And suppose we consider C double bond C bond H bond H. Suppose we have here CH3. Suppose we have here CS2 CS3. Now, dear students, what's happened here? This is less electronegative to more electronegative. This is the direction, this is the direction. Okay, no problem, this is direction. But see, both have the same sign, but magnitude is different now. So this is the direction, this is the direction. No doubt opposite, but it is not equal to 0 now. Why? This might maybe have plus 0.8, this might maybe have minus 0.5, because this is ethyl group, this is methyl group. It means overall not mu is not equal to 0. No doubt here also mu is not equal to 0, but this mu is always greater than this. The dipole moment of cis isomer is always greater than the dipole moment of trans, because maximally this cancel, but addition takes place of these two dipole moment which have a higher contribution in individual polar bond. So dear students, listen very carefully. So dipole moment of cis isomer is always greater than the what? Trans isomer. This is the first point. This is the first point. Okay. Now what is the second point? Suppose two different group is there. Two different group means what? Suppose I have C double bond C. Suppose I have here Cl. Suppose I have here CS3. Suppose I have here EH and here H. What we people say? This is the molecule which is called as the trans molecule, because two identical group is on the opposite side. HH is on the opposite side. Therefore, indirectly we people says that this molecule is the trans. And suppose for example you see C double bond C. Listen very carefully. This is Cl. This is Cl. Sorry, this is what? CH3, and this is H. This is H. This is the cis molecule. Now, if two group have a opposite inductive effect. Opposite inductive effect means what? You write down which word I am used here. This is very important to you. These two group have opposite inductive effect, that less electronegative to more electronegative. Electronegativity of Cl is greater than C, but electronegativity of CS3 is less than C now. This is greater than C, this is less than C. It means that this is opposite now. This is opposite inductive effect, opposite, less electronegative, more electronegative. If this is less electronegative, then direction is this, because see, this is more electronegative and this is more electronegative, direction is this. It means both have the same direction. Addition of this dipole moment takes place, but in this case, this is the direction, this is the direction. Both have opposite direction. So this dipole moment subtract from this. So my dear student, the dipole moment of this is always greater than this now. It means that dipole moment of trans is always greater than cis. What time? If two groups have opposite inductive effect. This is the very interesting and very important phenomenon. Whenever two groups have opposite inductive effect, then at that time the dipole moment of trans form is always greater than the dipole moment of cis form. So this is the very interesting concept related to you by considering dipole moment phenomenon. Now the dear student come towards the third case. As per my idea, you don't have any problem related with the third case. I will give you all, sorry, this is third application. Now we are in the fourth application of dipole moment. Keep in your mind, fourth application. Which one is the first application? The first application is that to decide the geometry and polarity of molecule. If mu is equal to 0, then the molecule is non-polar that have a planar structure. If mu is not equal to 0, then molecule is non-polar and that have a non-planar structure or unsymmetrical structure. The second application we are completed the calculation of percent ionic character. How to calculate percent ionic character? Percent ionic character is equal to experimental value of mu divided by theoretical value of mu into 100. How to calculate the theoretical value of mu? Experimental value they are given in the problem or numericals. Theoretical value we calculate by using the formula mu is equal to Q into D. So by using this phenomenon you just balance the unit and then automatically you got the answer of that question. And finally the third application to identify cis and trans isomer or to identify the cis and trans geometry. And the last application concept, the last application fourth, to locate the position of substituent in aromatic compound. Dear student, listen very carefully. To locate the position of substituents, in aromatic compound, to locate the position of substituents in aromatic compounds. This is the very interesting and very important phenomenon related to this dipole moment concept, to locate the position of substituent in aromatic compound. Now dear student, if the same substituent are present unsymmetrical position, so mu is always inversely proportional to the bond angle. Inversely proportional to the bond angle means what? Suppose I have this type of molecule, if here one Cl, here one Cl, these two Cl exactly on opposite position, therefore bond angle is 180. You got it, bond angle is 180. And actually what is the this is direction exactly cancel to each other, mu is equal to 0. Now if in place of para isomer we have a meta isomer, now we cannot perfectly cancel the dipole moment. Here bond angle is how much? 120. If bond angle is 120, then mu is, and suppose for example we have orthodichlorobenzene, then mu bond angle, how much bond angle? The bond angle is 60. Okay. Now dear student, it is inversely proportional to the bond angle, na? Therefore dipole moment of this is always greater than this, so as per my idea you don't have any problem related to this phenomenon. So these are the very interesting concept which we are completed as a dipole moment. I hope use this dipole moment, read very carefully, see all the video very systematically, then you able to solve any question from any book, because all the questions are very simple for your consideration. So as per my idea, this is the very interesting part related to the dipole moment. Now till now we are completed all the property related with the covalent bond. Now I am moving toward the next and very important part of this topic. Some bonds is there. That next bond is called as the coordinate bond. Finally that one is called as the hydrogen bond. Then some properties of hydrogen bond. Now some related all this concept. But before going to discussing, now I am going toward the next theory of this topic, because in previous videos we completed molecular orbital theory, we completed after that molecular orbital theory, the next point that one is called as the hybridization. After this hybridization, another next point which we are completed inside of this phenomenon, the another next point which we are completed in this theory, that another next point is called as the what? Hybridization, in types of hybridization. Then after hybridization, very interesting concept, that one is called as the valence electron pair repulsion theory. And after valence electron pair repulsion theory, that one is dipole moment. Now the next theory are present in your syllabus. The next theory is called as the molecular orbital theory. Dear students, I hope you must be very serious with the molecular orbital theory, because I know the molecular orbital theory is something complicated as compared to valence bond theory or hybridization or all these things, because only 2 points in the chemical bonding is very important. Once if you know the molecular orbital theory, this is called as the MOT, molecular orbital theory. My friend, my student, listen very carefully, because maximum time they ask the question on the basis of molecular orbital theory, and this is called as MOT. What is mean of MOT? Molecular orbital theory. Now, which are the important aspects related to the molecular orbital theory? Which are the important consideration? I will give you some basic idea to you before going to start real molecular orbital theory. I will explain you some important things. Now, actually, molecular orbital theory is very important in inorganic chemistry, in coordination chemistry also. What is the meaning of molecular orbital theory? When suppose for example we have, I will give you an example dear student, before going to define you what is the real MOT, you see toward the board, this gives you 100% idea, or this clear all these things which confusing all the point which are confused to you, or if any you have a confusion in your mind. See friends, now dear student, this is the H2 molecule. How the H2 molecule is formed? By using 2 hydrogen. Listen, what is difference between this and this? The difference is that these two are atom and this is the molecule. Yes, you know very well. Now listen, these two are the atom and this is the molecule. What is difference between atoms and molecules? Because now in this case hydrogen electronic configuration is 1s1, this is 1s1, but in H2 molecule electronic configuration become like this. Means what? Whenever the electron present in the atom, then that electron, whenever electron present in orbital of atom, then such orbital is called as the atomic orbital. This is called as the atomic orbital. What is the meaning of atomic orbital? Atomic orbital means the orbital of that particular atom, or the electron containing orbital of the atom is called as the atomic orbital. But when these two atomic orbital are mixed together, listen very carefully, because the introductory part of the molecular orbital theory is very important. When these two atomic orbitals are mixed together, then atomic orbital is converted into the molecular orbital, obviously na. When atomic orbital are mixed together, then automatically atomic orbital converted into molecular orbital. This is very interesting phenomenon. Means atoms are mixed together and this gives molecule. Then how the molecular orbital is formed? This is very important. Now friends, in H2 molecule, we have a 2 atomic orbital. This is one atom of hydrogen and this is the another atom of hydrogen. We have a 2 atomic orbital. Listen, this is a very interesting rule present in molecular orbital theory or mixing theory. Number of atomic orbital are mixed together, that gives same number of molecular orbital. You keep in your mind. This is the very golden word which I use in front of you. The number of atomic orbital are mixed together, that gives the same number of molecular orbital. Is it okay? Now, number of atomic orbital are mixed together, that gives the same number of molecular orbital. Means what? Suppose in the formation of H2 molecule, we have a 2 atomic orbital. 2 atomic orbital gives 2 molecular orbital. Okay. Out of 2 molecular orbital, 1 molecular orbital have a lower in energy. 1 molecular orbital have a lower in energy. Suppose this is the energy diagram. This is a 0 energy. This is minus. This is plus. Those molecular orbital which have a lower in energy, such a molecular orbital is called as the bonding molecular orbital. This is called as BMOs. What is BMOs? This is known as bonding molecular orbital. And another atomic orbital have a higher in energy, and this higher energy atomic orbital is called as the anti-bonding. This is called as, this orbital is called as anti-bonding molecular orbital. This is called as what? Anti-bonding molecular orbital. It means, is it okay? Suppose for example, I have a 2 molecular orbital, then 2 molecular orbital overlap to each other. It gives, I have a 2 atomic orbital. These 2 atomic orbital are overlap to each other, gives 2 molecular orbital. Out of 2 molecular orbital, the one orbital is called as the bonding molecular orbital, another orbital is called as the anti-bonding molecular orbital. What is the bonding molecular orbital? Write down in your notebook. I will give you all the important aspects related to this phenomenon. Each and every point write down in your notebook, because this concept is very important. What is the bonding MOs? The bonding MOs which have a lower in energy as compared to atomic orbital. It means that those orbital which is those molecular orbital is the bonding molecular orbital which have a lower in energy. See, the energy of this BMOs is less than this, And what is anti-bonding molecular orbital? Anti-bonding molecular orbital is that molecular orbital which have a higher in energy than atomic orbital. So my dear students, my friends, tell me, out of these two, which one is more stable? Obviously bonding is more stable, na? And that's way when two atoms are approached to each other, the energy releases, because see, this is a negative point. These two atoms loses its energy, and after losing the energy, such molecule is formed, and that's way that molecule is more stable than the atom. Is it okay? Now dear students, then each atomic orbital we have a 1 electron. Then now feel that electron of atomic orbital in molecular orbital, now because obviously when atomic orbital are converted into molecular orbital, then electron present in the atomic orbital that automatically enters in the molecular orbital. Now how to fill the electron in molecular orbital? The filling of electron in molecular orbital takes place strictly according to the Hund's rule, above principle, Pauli's exclusion principles. So what a Hund's rule or what above principle says that according to above principle, the filling of electron takes place by considering the energy of that orbital. The energy phenomenon is very important by Pauli's exclusion. Now my dear student, the energy of BMO is greater than ABMO, that is anti-bonding. So both electrons are enters in bonding orbital, not. So this is the very simple conclusion. This is the very simple explanation related to molecular orbital theory. Now suppose dear students, we have a such a 2 atomic orbital. Then these 2 atomic orbital gives 4 molecular orbital. Out of 4 molecular orbital, 2 molecular orbital are bonding and remaining 2 molecular orbital are bonding. That is, if listen very carefully, if atomic orbital is even, then if atomic orbital is even, then suppose if even, suppose atomic orbital we represented by n, suppose atomic orbital we represented by n, and if atomic orbital is even, then molecular orbital is equal to, then molecular orbital, how to calculate molecular orbital? Therefore bonding MOs, that is bonding MOs is equal to n by 2, and anti-bonding MOs is also is equal to what? Anti-bonding MOs is also is equal to n by 2. Okay, suppose we have a 4 atomic orbital, then out of 4 atomic orbital, 2 are bonding, remaining 2 are anti-bonding. Suppose we have a 6 atomic orbital, out of 6 atomic orbital, 3 are bonding, remaining 3 are anti-bonding. Suppose we have a 8 atomic orbital, out of 8 atomic orbital, the 4 are bonding, remaining 4 are anti-bonding, if it has a even, okay. And if atomic orbital is odd, my friend, listen very carefully, if atomic orbital is odd, if atomic orbitals is odd, because so many orbitals is there, then at that time in molecular orbital, bonding MOs, dear friends, bonding MOs is equal to n minus 1 by 2. Same things happens here. How to calculate anti-bonding MOs? Anti-bonding MOs also n minus 1 by 2, and 1 is remain, and that remaining 1 MOs is called as non-bonding MOs, non-bonding, which have a 0 energy. This is non-bonding. I will draw the picture of non-bonding. My friend, suppose I have 3 atomic orbital containing molecule, 3 atomic orbital. Out of that 3, 1 is bonding. Out of 3, another 1 is bonding, and 1 is called as the non-bonding. This is BMOs. What is BMOs? Bonding molecular orbitals. This is ABMOs. What is ABMOs? Anti-bonding molecular orbitals. And this is NBMOs. What is NBMOs? Non-bonding. The orbital which is not involved in the bonding, that have a 0 energy. Now this is 0 energy. This is decrease. This is increase. Therefore, non-bonding molecular orbital have a 0 energy. Why? This orbital does not involve in the bond formation. So these are the basic consideration required to you by considering the molecular orbital theory. Then what is the real molecular orbital theory? We will discussing in the next video. Thank you very much.